Hey guys, welcome back. So we have the second video for differential equations. Hopefully you had some success with the first one, and hopefully you had some success with the homework. Definitely go on and check out the solutions if you haven't already, just because some of the guys that submitted them, we did some good work, but we definitely have some answers to check as well. Okay. Some of that stuff can be a little bit tricky when you've got all of it in front of you. So again, double check my solutions versus yours. Please make sure you get this stuff down, especially the last video. That's like home run content, in my opinion, in terms of getting questions correct. Okay. So today's main goal is we're going to move forward into solving differential equations analytically. And there's a special method that we're going to use called separation of variables. What we did last class, or what in the last video, was we actually solved differential equations, and I put quote unquote solved because they were more approximations, because that was the graphical solution. And so we can't be perfect with the graphs that we draw or sketch, but we can get really close. And so that was the graphical solution. Today, we're going to find the exact solution to differential equations. And again, by using this method called separation of variables, and we'll see why it's called that in just a little bit. Just have this note here. We, again, are only going to be working with first order separable differential equations, meaning that we'll be able to separate the variables x and y on opposite sides of the equal sign easily, and in a way that we can take integrals of both sides. So just a little bit of a highlight as to what's to come. Okay, but that's what they're called, first order separable differential equations. There are other methods in higher level differential equations used to solve first order non-separable differential equations, or second order separable differential equations and non-separable, so on and so forth. The problems that we're mostly going to be working with today is something called initial value problems. And really what that means is that we'll have a differential equation, but we'll also have some initial value in the form of an xy coordinate, or an x value and a y value. And what that's going to do is it's going to force us to find the exact curve that goes through that point. So in just a second, we're going to talk about no longer having a family of functions. It's going to be one specific curve. Think about that slope field. You could have drew an infinite number of solution curves through any of those paths, but I want to find one in particular. So you have to find the exact curve that the problem is set up to find. Okay. We are going to be using integration as the main operation to solve these. How do you undo a derivative, which a differential equation is you use integration. So we are going to use integration. And we know that with integration or anti-differentiation comes that plus c. And so the initial value is going to help us and allow us to find what c is actually equal to, so we can come up with an exact y equals solution. Okay, and that's called the particular solution. So you'll see that term thrown out a lot, a particular solution, not a general solution. A general solution would have that plus c. Okay, just an idea, just to further cement what I'm talking about. We saw this exact slope field. It was actually the first one I ever showed you in the first video. I had told you that it looks very similar to what, y equals x squared plus c. That slope field would look like. It's not exact, so don't quote me here. I know the two should line up much closer to like 5. So I just an example. Don't quote me here, but I'm just trying to get it through. What we want to do is, this is a general solution, y equals x squared plus c. I want to find the exact curve, so the equation for this curve that goes through the point 0, 1. So it does go through that point, and it looks like, it might be something very close to y equals x squared plus 1. This is graphical, so it's an approximation. We will find the exact solution today. Okay, so I'm going to do this in basically 3 examples. So each example will follow the same basic steps, but each example has its own unique piece to it. And so that's why I picked the 3 that I did. And then I have 2 try on your own problems, which I'm going to encourage you to pause the video and try it, and then come back and I'll explain the solutions as well. Okay, so it's actually a total of like 5 examples for today's video. And I think that that's the best way to do this, because again, once you do a couple of these, you start to get into a rhythm, and hopefully you feel pretty good about it. All right. So I'm going to show you 3 different ways in which the problem might be set up or the information might be given to you. And so here's my first one. Given the initial condition y of 1 equals 0, find the particular solution of the equation dy dx equals 2x over e to the y. Hopefully that differential equation looks familiar to you. It was the first one that I ever showed you in the very first video. And if we were to go back to it, so if I scroll up here, give me a second. I told you that the answer, so the actual solution to this differential equation, is the natural log of x squared. All right. I did not give you an initial condition here. Technically, I should have in order to get this answer. But I am with the initial condition that I just gave you for the one that we're about to do, this will be the answer. So I'm going to show you how you get from here to here. I had only told you that it works because when you take the derivative of the solution and use that equation, y equals ln of x squared, in the differential equation, the two matched up. So I told you that's what a differential equation looks like and means and how you solve it. But I'm going to show you the exact way to get to the natural log of x squared today. All right, so let's get back to it. All right, so first 2 steps are always going to be exactly the same for us. And so this is where the method of separation of variables comes from. The very first step is we separate the variables, right? So we want to take all the x's over to the, this should say right side, and then all of the y's over to the left side, okay? It actually doesn't matter which side you bring them to. If you bring it to, the y's to the right and the x's on the left, it doesn't matter, but this is more familiar to us having a y on the left and an x on the right. So that's what we'll stick to. Okay. And when I say variables, I also mean the dx and the dy. So I want the dx on the right-hand side and the dy on the left-hand side. All right. And so that's what this looks like, right? So if I go up here, this top equation, you just use algebra to get pieces from one side to the other. So I'll have to multiply both sides by e to the y, and then I'll have to multiply both sides by dx. If I do that, I end up with this equation. Okay. From there, my goal is to solve the differential. In order to get rid of the differentials, which are the dy and the dx, I have to integrate or anti-differentiate, right? So those are inverses of one another. We know how to integrate functions now of all kinds, and so those skills are going to be put to the test. And so what happens when I integrate both sides, right? Which I'm allowed to do because integration is an operation, and I know with equations, whatever I do to one side, I have to do to the other, and if I do that equally, then the equation stays true. So left-hand side, e to the y, I know its antiderivative is just e to the y again. And again, I'm keeping that as a y because I'm integrating with respect to y. So that was e to the x dx. It would be e to the x plus c, but it's e to the y dy, so it's e to the y. And then notice I'm putting a plus c sub 1 for its constant. And then on the right-hand side, pretty simple power rule, 2x squared over 2 plus c sub 2. So it has its own constant. All right. So continue on here. First thing I want to talk about is this plus c. All right. So go back one more. Notice that there are 2 plus c's there. They are both random constant values, so random numbers. Again, this is an equation, so technically I could subtract c sub 1 from the left-hand side over to the right-hand side. And so c sub 2 minus c sub 1 is just another random constant. And if you think about it, if that's the first 2 steps for every problem that we do, that's going to happen every time. And so there's really no reason to have 2 random constants throughout all of your problems. In fact, this is the only example I'll do that you see a c sub 1 and a c sub 2. From here on out, I'm just going to keep 1 plus c on the side with the x's, right? And again, that should say right side. So whenever we go through these, you don't have to add both plus c's, just one of them, and that'll take care of the whole equation, okay? So just 1 plus c on the right-hand side with the x's. Again, you could keep it on the y's, but just for continuity for us, let's just keep it on the right, and I think that'll make things easier for us, okay? All right, so at this point, we remember the goal, right? So the overall goal is to get an equation, y equals something in terms of x, all right? So some function in terms of x. I want to eventually solve for y, but I also have to solve for c. So and before I solve for y, a total, then I have to find c, and this is where the initial condition comes in. My initial condition, which I put right over here, was y of 1 equals 0. Remember, this is your input, so your x value is 1 and your y value is 0. For your third step, it's actually up to you when you decide to use your initial condition. Technically, you could solve for y and have it, again, that's a general solution because that plus c would still be in there. You would take the natural log of both sides, but then you would have to solve for c after solving for y, in which case you probably just have to undo what you did to solve for y. So a lot of the times it's actually easier to just wait to solve for y, use your initial condition to find c, and then solve for y. So for, I think, the 3 examples that we do today in the try on your own, so that's the method I'm going to take. You can certainly, depending on the problem, if it is easier to solve for y and then solve for c, do that. It's not wrong. It's just, again, something that you just have to make a judgment call on. But again, I'm going to show you how you can do it pretty much by not solving for y first, solve for c, then solve for y. So what does it mean to use your initial condition? Well, if x is equal to 1, y is equal to 0, I have y's and x's right in here. I'm just going to replace those values up top. So e to the 0 equals 1 squared plus c, right? X equals 1, y equals 0. These are now numbers. E to the 0 is 1. 1 squared is 1 plus c. I can easily solve for c. In this case, c equals 0. Okay, once you find c, you're going to go back up to, you're going to go back up to this equation right here. Replace your c that you just found with this c and solve for y. So fourth step, replace c. And this is important. I need you to, so we decided to solve for c before we solve for y. Whenever you find c, you need to replace c where you began solving for c and then solve for y. Okay, so in other words, if you were to go back one slide and you say you found c equals 0, but then you said, you know what, I'm going to solve for y, and then I'll plug in c at the end, right? You can't do that, right? Because it might change your answer. Wherever you started solving for c, which was right here for us, plug in c then, all right, and then finally solve for y. Don't solve for y, then plug in c, solve for c, plug in c, then solve for y. So if I plug in c equals 0, e to the y equals x squared, take the natural log of both sides. The natural log and e are inverses of one another, so those cancel each other out, and all I'm left with is y is equal to the natural log of the absolute value of x squared. Okay. Please remember to put your absolute values, all right? Or else these answers are A, incorrect, and B, might not work out for you, all right, when you have to decide if you did the problem correctly or not, okay? So there's my answer. Y equals the natural log of x squared, which we knew would work. Okay. All right, let's look at the second example. So a little bit different setup in terms of how the problem is worded, but it's actually the exact same type of problem. So I need to find the equation of the curve, which we talked about, the singular particular curve that passes through the point 1, 1. There's your initial value, x, y, and has a slope of y times x squared plus 1. Doesn't say dy dx or y prime or anything like that, but you have to know that, right? If it's saying the slope is y times x squared plus 1, that's a derivative, differential equation. So dy dx does equal y times x squared plus 1. All right, and then it furthermore tells you that that is the slope at any point xy, which is nice. All right, so we're going to go through this one maybe just a little bit quicker because I think we've got the steps down, or at least we went through them once already. And so I'm going to reveal some at a little bit at a time here to not overwhelm us with stuff written on the page. So here is my initial setup. Here's my initial differential equation. My first step is always to separate variables. So if I separate variables, what does that look like? Well, now I've got all my x's on one side and all of my y's on the other. So I'll divide by y and then multiply by dx on both sides. Once I separate the variables, my next step is to integrate both sides. And this, again, both easy antiderivatives for us at this point. If you're not seeing this part right here, this is really 1 over y times dy, right? So 1 over y dy, it's the exact same thing. We know the integral of 1 over x or 1 over y is just the natural log. And so the next part is the natural log of y equals x to the third over 3 plus x plus c. All right, so using the power rule on the right-hand side again. All right, once we have this part, now it's time to find c. So we find c using my initial value of 1, 1. So at 1, 1, what does the equation look like? Replace y with 1, replace x with 1. We get the natural log of 1 equals 1/3 plus 1 plus c. And look at that. I'm actually noticing that I messed that up a little bit. I'm going to pause the video and fix this and be right back. Okay, I'm back. Sorry about that. Had to fix that. I accidentally made that a 1/3 plus 1 equals 2. Which does not make sense. So change this to 1/3 plus 1, which equals 4/3. So 0 equals 4/3 plus c. We subtract 4/3 from both sides, get c equals negative 4/3. And then I'm going to resubstitute that c value into my initial solution, my initial general solution, which is right down here. And I'll solve for y. So if I initially plug in c equals negative 4/3 in for c, this is what it looks like. And how do I solve for y? Again, the exponential and the natural log are inverse operations. And so technically I would exponentiate both sides. So e here and e here. And these two would go away. And I would be left with e to the x to the third over 3 plus x minus 4/3, an exact solution. All right. Hopefully you're getting the hang of this a little bit. Let me know if you don't. Jump on the video, and I'm happy to answer questions. Let's go into the third example. So this is a good one. Using some trigonometry here. And it's a nice solution, but this one offers a really unique piece to it, which you absolutely need to know how to do. And so the beginning is exactly the same. However, again, just notice that there's a slightly different setup wording to the problem. So we're given a differential equation. One of the bigger differences, again, is that I have a different way of recognizing that it's a differential equation. I don't see a dy dx, but I do see a y prime. As soon as I see that derivative notation in any way, shape, or form, it's a differential equation. And I want to find the particular solution for y equals f of x, right? So I want to find the exact function that has an initial condition or goes through the point pi over 4, 1, right? Input, output. All right, so we will start off the same way that we have before. So here is my differential equation, separating the variables a little bit. So I subtracted the sine x over. I changed y prime to dy dx because we're going to have to move that dx over. And then I kept the 3y on the left-hand side. I will multiply both sides by dx to get all of the x's on the right-hand side and all the y's on the left. Finally, I will integrate both sides. So once I integrate both sides, again, we know how to do both of these integrals or antiderivatives. I'm left with 3y squared over 2 on the left-hand side, and then a positive cosine of x on the right-hand side, okay, plus c. Because again, remember the integral or the antiderivative of sine is negative cosine, so negative times a negative cosine is positive cosine. Again, remember that I do not have a plus c on the left-hand side, just on the right, one singular random constant. Okay, once we find that random constant, our job is to once we see the random constant, our job is to find the random constant using our initial value. So my initial value is pi over 4, 1. I'll plug in pi over 4 for x and y for 1. And when I do that, I get 3 times 1 squared over 2, cosine of pi over 4, plus c. Yes, you may need to know some unit circle here, right? So cosine of pi over 4, I know is the square root of 2 over 2, and then 3 times 1 squared over 2 is obviously just 3 halves. I'll subtract square root of 2 over 2 from both sides. And once I do that, I get c is equal to 3 minus the square root of 2 over 2. All right. So since the denominators are both 2, I don't need to find a common denominator. I can just make that one singular value. All right. In some cases, you may have to find a common denominator. All right. So just keep that in mind if you're subtracting fractions. But this time it worked out nicely for us. Once we find the c value, we're going to plug that c value back into the spot where we started to solve for c, right? So I started to solve for c right here. And so you'll see this c get replaced with this term. All right. So let's see what happens. Right, so there it is. There's my c value that I replaced. The x's and the y's come back, and I start solving for y in any way that I can. All right, this one takes a little bit longer to solve. We have to do a few steps, right? So the first thing I see is that I want to get the y by itself. So I'm going to multiply by 2 on both sides. I'll multiply the entire right-hand side by 2. You'd have to distribute. If you do distribute, recognize that the 2 gets multiplied by cosine, and then the 2 gets multiplied by this fraction. Those denominators, the numerator and denominator, will simplify one another. And so once we do that, we'll have 2 times cosine plus 3 minus the square root of 2. And then I need to divide by 3 on both sides. And so I get just y squared is equal to 2 cosine plus 3 minus square root of 2 all over 3. So the whole thing. And then finally, I need to take the square root. However, this is the unique part. Notice that I still need to keep that, I need to have that plus minus there, right? Because I know whenever I take the square root of both sides of an equation, it's possible that it's either a plus or a minus, right? That's something you've done plenty in the past. So the goal, the last part of this example, and this is why, again, why it's unique, is I need to figure out whether there's a plus or a minus there, because technically this is 2 different functions. And the goal of this problem is to find one singular function. So how do I do that? Well, I have an initial condition, meaning that when I plug in pi over 4 for x, I have to get positive 1 out. Now, that does not mean that this is going to be positive square root all the time. All right, and we'll kind of see that in just a second. Typically, it will be, though, if your y value is positive, the square root obviously can't be negative, and so you should be using the positive. However, how do you definitely find out, or how might this become valuable in other situations where you're not sure what to do? You can plug in your x value and actually solve the right-hand side. As soon as you get down to a spot where you know you need to get positive 1 as an output, you choose the sign that's correct. Okay, so here's my initial starting point, what I just found from the last slide. I'm going to plug in my initial x value of pi over 4, 2 times cosine of pi over 4. Well, cosine of pi over 4 is square root of 2 over 2. So those 2's will eventually cancel. If I come up here, I get the square root of 2 plus 3 minus the square root of 2. The square root of 2 and the square root of 2 will cancel. I get 3 over 3, which is just 1. Now I get plus or minus the square root of 1. Go back to your initial value. You know your initial value was a y value of a positive 1. So you're going to keep the positive square root of 1. And finally, basically, you can just get rid of that positive value there. Okay. And there you go. That's your answer. Okay, so here are my 2 try on your owns. I'd like you to pause the video now and give it a shot. I have the solutions to both of these on the next 2 slides, which I'll go over briefly. If you have further questions, again, jump on the video, let me know, or go into the Google Doc. Okay, give it a shot. All right, here is the solution to the first try on your own, Toyo. All right, so again, I'm not going to maybe go in as much detail, but here are all the steps. You can see that I'll always start with separating the variables. I actually didn't even write the integral signs here. We would have to integrate both sides of this problem right here. Okay. Once I integrate both sides, here are my antiderivatives. Once I find my antiderivatives, I need to start solving for c by plugging in my initial value for both x and y. So here's y equals 2, x is equal to 1. I solve for c just using algebra. So c equals negative 5/8 in this case. Once I find negative 5/8, I need to plug that back into where I started solving for c, which is right here. Okay, so that takes place right up here. Once I plug in my c value, I start solving for y in any way that I can. For this one, I first multiplied by 2 on both sides, got rid of this 2 as a denominator, reduced this to a 4, and then I noticed that I have y squared underneath of 1 right here. So an algebraic technique that we can use is really just reciprocating both sides. So I'll reciprocate negative 1 over y squared, you just get negative y squared, and then take the reciprocal of the right-hand side, which is really just putting 1 over x minus 5 to the 4th. Next thing I do is divide or multiply both sides by -1, so that's where the negative comes from, and then I have to take the square root of both sides. Again, you have that plus minus, so how do we figure out which one to keep? We should be pretty certain that it's plus because this is a positive 2, not a negative 2. But just to make sure we did everything correctly, we'll plug in my initial y value of 1 into this spot right here. All right. And so that's what happens over here. I get negative 1 over 1 minus 5/4. This is really 4 over 4 minus 5/4. And so that should give me okay, sorry about that. I actually had to pause the video again. I'm having an off day here. So 1 minus 5/4 is negative 1/4. And so if I have 1 over negative 1/4, I can just reciprocate that. So it becomes a positive 4. Square root of 4 we know is 2. I know I need a positive 2, so I'll keep the positive sign. Everything works out. And so my particular solution works. Okay. All right. One more, and then the video's over. Actually, we're all done. So second try on your own is here. This one was a little bit more interesting as well because there's a lot of natural logs and things of that sort. So separate your variables. dy over 1 plus y equals dx over x. Take the integral of both of those. Technically, on the left-hand side, this is actually u substitution, but the derivative of 1 plus y is just 1 with respect to y, so you don't actually see it. But keep in mind that you may have to use u substitution in some of these problems, right? That's a technique how in terms of integration, and so you may be asked to use that. All right, we'll do some of those eventually, but today was just sort of the intro. So natural log 1 plus y equals natural log of x plus c. We'll start finding our initial value from here, plug in 1 for y and negative 1 for x. So natural log of 2 equals the natural log of the absolute value of negative 1. Again, that's why it's important to make sure you have the absolute value or else you're going to get tripped up there. So I know the natural log of 1 is 0, and so really I just get c equals the natural log of 2. Once I know c equals natural log of 2, I'll plug it back into where I started solving, which is the second step right up here, and start solving for y. So natural log of 1 plus y equals natural log of x plus the natural log of 2. First thing I need to do is take the exponentiate both sides of this part right here. So if I take e here and then e here, this whole thing goes away, and I get 1 plus y equals e to this long piece here, the natural log of x plus the natural log of 2. Here's a little bit of a tricky part. However, this comes up a lot with differential equations, and that's laws of exponents, right? So I know that if I have a base and its exponents are being added, I can kind of work backwards with a property of exponents, which says if I'm multiplying two values with the same base, which is e and e, then I can add the exponent. So I'm just going to go backwards, actually. And what that allows me to do is it actually allows me to simplify both of these e to the natural logs individually, right? Again, they're inverses, so that goes away and that goes away. And so I just get 1 plus y equals 2 times the absolute value of x. And so now all I have to do is subtract 1, all right? And I get y equals 2 times the absolute value of x minus 1. And that's it. Okay, so hopefully this was a good video for you. Hopefully you understood the steps. There's a lot of algebra and simplification techniques here. So if you have any questions on those, please let me know as soon as possible so I can help you out with them. Here's what's still to come. Next time, since we know how to separate variables, we're going to talk about modeling exponential growth and decay with differential equations. That's sort of like the special area that we learned this year. And then we'll take a look at a couple of free response questions and what extension problems might be asked through these, right? We are talking about derivatives. So again, we might be talking about things like concavity. We might be talking about linear approximations. And then might be talking about increasing, decreasing levels, so on and so forth. So all that stuff is going to come into play, and we'll take a look at a couple of examples of that. Finally, homework's on by Malvern. Hope you guys have a great day, and I'll talk to you soon.